Professor Su mentioned, what I'm particularly interested in at the moment are contact hypersurfaces in Hermitian symmetric spaces, but I don't really understand them well, so I started to try to understand how actually I try to understand contact hypersurfaces in a more general context in Kaehler geometry. So in fact, contact geometry is something, it's geometry on some even odd dimensional manifolds. Maybe to remind you of what a contact manifold is, what we need is an odd dimensional smooth manifold, and then M is a contact manifold precisely if there exists a one form eta on M such that eta wedge d eta, so d eta is a 2 form, so we wedge n minus 1 times, so that's a 2n minus 1 form. Precisely the dimension of the manifold is non-zero. Okay, and so this form eta then is called a contact form, and the distribution C, which is defined by the kernel of eta, so eta is a one form, so this is a distribution in the tangent bundle of M, and the rank of this is just codimension 1, yeah, because it's a one form, and that's called the contact distribution. On the manifold, and this condition geometrically means that somehow the maximal dimension of integral manifolds to this contract distribution is just n minus 1. Yeah, so it's somehow this contract distribution is somehow very far away from being integrable. And I want to discuss one example. This is a really good example, and it's elementary. It's the n minus 1 2n minus 1 dimensional sphere of radius r. So we take all points. What do we take? Say x in Cn, for which the length of x squared is equal to r squared. So we take the sphere of radius r inside of Cn, and that's a contact manifold. And I want to go through proving this in the next 5 minutes. So on Cn we have this standard inner product. Yeah? So we have Zw is the real part of the sum of, we take the coefficients Z nu multiply with W nu, so these are the coefficients. We take the bar here, and I think that's it, nu equal from 1 to n. So that's the standard inner product, which gives us here the norm, which I used here. And then on the sphere, so let's draw the sphere. So we have radius r, and we take a point, so r. So here is a point, say this point is z, and then we have a unit. So we get a unit normal vector here, say psi z equal to, so I take, well, psi z is equal to 1 over r times z. So this gives us a unit normal. And then we get a tangent vector by multiplying this with the complex structure, or with the I on Cn. So here we have I. In fact, I don't want to call this psi. I think I want to call this n. And then here we get psi z, so I multiply this with I. And then for some maybe sentimental reasons, I multiply this with -1. Okay, so what we get is a tangent vector, psi. So this psi gives us a vector field on the sphere. And we get, with respect to this metric, a dual one-form eta. Yes, so we define eta of x is just x, inner product of x and psi. This gives us a one form. Now I want to calculate now explicitly d eta in this special case. And what I want to introduce for this is just the Kaehler form on Cn, which is just given by I times xy. So this is the usual Kaehler form on Cn. And now let's start to work out d eta. So you get d eta by definition. We first differentiate eta of y with respect to x. Then we differentiate eta of x with respect to y, minus this and minus eta of the bracket of x and y. Need a different one. So eta of y, so this is just the inner product of y with psi. So this will give us an nabla xy and a psi plus y, and then here we have nabla x psi. And then the same with x and y interchanged with a minus nabla y x psi minus x nabla y psi, and then minus the bracket of xy inner product with psi. And this nabla is just the usual derivative of Cn, and we see because this is torsion free, so this vanishes, this goes to 0. So we are left with this one. So we differentiate now psi, but psi is just I times the position vector, when the one is 1 over r and with a minus. So when we differentiate this, what we get is minus 1 over r, and here we have a y, and this is all linear then because we are in Cn. This is I times x, and minus, that's a plus 1 over r x times, and then I times y. So I can put this maybe on the other side, the I here. So what I get is minus 2 over r ix times y, and this we see we can express in terms of the Kaehler form. So this is minus 2 divided by r times omega of xy. Yeah, so d eta is just a multiple of the Kaehler form. So what we get is d eta is minus 2 over r times the Kaehler form. Now the Kaehler form has a maximal rank, and in particular here on the contact distribution. So what's the contact distribution? Well, we don't have it yet because we don't know it's a contact thing, but what we have to look at is the orthogonal complement of z and iz. When we restrict omega to this has maximal possible rank. Yeah. So what we get is here, so eta wedge d eta to the power n minus 1 is minus 2 over r to the power n minus 1 eta wedge omega to the power n minus 1. Now this is non-zero on the orthogonal complement of psi, and then we have eta, which is 0 exactly on there. So when we put everything together, we get that this is non-zero. Yeah, so this is the standard proof to show that the sphere is a contact manifold, an odd-dimensional sphere. Yeah, but the interesting part about this is the proof, yeah, analyzing the proof, because what we now can do is try to imitate this, or try to look in a more general situation, replace Cn by an arbitrary Kaehler manifold, you look at the hypersurface in there, yeah, and then you just ask the question, when do we get a contact hypersurface through this process? Yeah. So it wasn't clear to me how this works. I think it's now a bit clearer. So so in the first talk today, I think I want to talk about the general situation where we have a hypersurface in a Kaehler manifold, and when does the Kaehler structure induce a contact structure? So a fixed sum notation, m bar n is then an n-dimensional Kaehler manifold. From now on. And then we take in there a hypersurface, a real hypersurface. And I always assume it's connected, not really important, but that's okay. And I also want to assume that it is oriented or orientable, so that I have a unit normal vector, a global unit normal field. Also, that's not important because all the calculations are more or less, they are local, so I can always achieve this. Yeah? But what I want is a global normal field. So then what we get is, I think Professor Perez mentioned this morning, what we get is an induced almost contact metric structure. Almost contact metric structure on M. Yes, so how do we get this? So this is just the, this is of course, so m bar n, so I should actually say, so what we've got here is also J is the Kaehler structure, or JG is the Kaehler structure. JG. Yeah, it's a metric together with the integrable complex structure, Kaehler structure. So G is then the induced metric, same symbol, doesn't cause any problems. Phi is just the tangential component of when we apply J to X, so X is in Tm. So this gives a nice tensor field on the hypersurface. Psi is just, so here is the normal field which I wanted, so N is a normal field, N unit normal field. On M, so we apply J to this, we get a tangent vector field, and then put the minus in front of this, and then eta is the corresponding metric dual one form. Yeah. So this is the almost contact structure, and then by construction the kernel of eta is just the maximal holomorphic subbundle of the tangent bundle of M, which in case that this eta becomes a contact structure will be the contact distribution. Yeah? So the kernel of eta is the maximal holomorphic subbundle of the tangent bundle. Okay. So here's so that's probably all familiar with. Then there is a definition. There is a useful 2 form on M. So it's the fundamental 2 form. The fundamental 2 form omega on M is defined by omega xy is equal to g of phi x y. So it's basically defined like the Kaehler form on M bar, but we just restrict to the tangent bundle, and instead of the Kaehler structure we use the induced tensor field phi. And the nice thing about this 2 form is that it is closed. And that's good to know. So that's our first, say, call it a lemma. The fundamental 2 form is closed. And I want to maybe at least indicate the proof, just to give you an idea of how to show this. So what we need to work out is this expression, the omega of x, y, z. So by definition, this is, well, I take the cyclic sum over x, y, z. So this is my symbol for taking cyclic sum of whatever comes after that. Yeah? X, y, z of, we have d omega of yz. So we differentiate yz. We differentiate this with respect to x and subtract omega of xy and then z. So this is how the omega is defined. So omega of yz, so this is just, if we insert our definition, g of phi y z. So we want to differentiate this with respect to x. What we get is again the cyclic sum, shouldn't forget this. So we first differentiate Laplace x phi y, inner product with z, plus, and then this one, g of phi y, Laplace z. So that gives this term. And then this one here is just minus g of phi of the bracket xy with z by definition. But this we can write as g of phi Laplace xy z minus g of phi Laplace yx z. Okay. So when we put everything together at the cyclic sum, then this becomes, so let me see what happens. Laplace x phi y z plus, and then I should have here minus g of phi Laplace x y z. So we get g of the derivative of phi Laplace x phi y z. So this gives these two terms together. plus, and then I get these terms, so it's best to put phi on this side, so then we get a plus here, plus these terms with phi on that side, so it's the same like there, and then we use a cyclic sum, and if one does this carefully, one sees everything vanishes, it cancels out. So we are just left with these terms, and then as Professor Perez this morning explained, it's very easy to get an expression for this, because phi just comes from J. Covariant derivative of J is parallel because we have a Kaehler manifold. One works this all out, this expression. It's not difficult. Yeah, so, and one term comes that this is 0. Yeah, so that's the basic idea. So the fundamental 2 form omega is closed. And that's true for any hypersurface in a Kaehler manifold. Okay. So now I come with the definition. So this m to n minus 1 contained in m to n bar, so it's the usual assumptions. Now that's a Kaehler manifold, real hypersurface. So it's called a contact hypersurface precisely if there exists a smooth and everywhere non-zero function rho on M such that d eta is equal to, for technical reason, it's 2 times rho times omega is the fundamental 2 form. So this is exactly the expression we had for the sphere in Cn, where this was minus 2 over r. So rho is minus 1 over r. Yeah? So we just imitate what we had for the sphere. Yeah, why is this really a contact manifold? So you see it's maybe a remark. So when d eta is 2 times rho times omega, then eta wedge d eta to the power n minus 1 is equal to, so d eta we can replace by 2 times rho times omega. So this will be 2 times rho to the power n minus 1 eta wedge omega to the power n minus 1. And then this fundamental 2 form on the maximal holomorphic subbundle, or on the, here in the case of the contact distribution, on the maximal holomorphic subbundle has maximal rank. Yeah, eta accounts then for the remaining dimension in direction of psi. So this all is non-zero. So that means that every contact hypersurface is a contact manifold, really. Every contact hypersurface is a contact manifold according to this original traditional definition. Yeah? Otherwise it wouldn't make sense to. Okay. So the first interesting result, and that's not trivial really, it's nice. So it's a proposition. I give it a number, proposition 1. So in this situation here, so when So suppose, actually this is the assumption, so when d eta is equal to 2 times rho omega, so we have this situation, and n is greater or equal than 3, then rho is constant. That always holds in any Kaehler manifold. Like we saw it in the sphere. In the sphere it's 1 over the radius, or minus 1 over the radius. And I want to prove this. Why this is. So d eta is 2 times rho times omega. We have got a nice equation. What do we do when we have a nice equation? Differentiate it. Okay, so what we get from this is that 0, so we take the second derivative, d squared, that must be equal to 0. So this is equal to 2 times d rho wedge omega plus 2 rho times 2 rho wedge d omega. No, 2 rho times d omega. But this is the fundamental 2 form, and we saw that this is closed. So this is 0. So it's just 2 times d rho wedge omega. Okay. Right, let's write this out explicitly. So this tells us we can forget the 2. So this means that 0 is equal to d rho of x times omega of yz. So I'm just writing down the definition of the wedge product. Plus d rho of y omega of zx plus d rho of z omega of x y. So omega yz, just this is the same as g of phi z, inner product of phi yz. That's the inner product of phi z with x, and that's the inner product of phi x with y. So we put x equal to xi. Insert y in the maximal holomorphic subbundle. Assume that the length of y is equal to 1 and put z equal to phi y, and let's check what we get. So we get 0 is equal to, here we get phi y, and z is phi y, because that's in the complex bundle. So z phi y has length equal to 1. We can cancel out the phi. So this is equal to 1. So we get d rho of x. Then here, phi z with x, this is 0, with xi, this is 0. And phi x with I, so that's phi xi. That's because phi maps xi to 0, so that's 0. So it's just d rho of x. So that tells us that when we differentiate rho in direction of the maximal holomorphic subbundle, we get 0. Sorry, d rho xi, yes. That's it, d rho xi. So when we differentiate in direction of xi, we get 0. So now, I haven't used the assumption yet that n is greater or equal to 3. That happens in the second step. So now we choose x in the maximal holomorphic subbundle. Now since n is greater or equal than 3, we can choose y in the maximal holomorphic subbundle. Again, we assume it has length 1. Such that y is perpendicular to x, and it's also perpendicular to phi x. Yeah. standard thing to do. So then we put z equal to phi y and see what we get. 0 is equal to, so we insert this. So d rho, here we have x, g of phi y and z, phi y and z, so y, d rho x, phi y is this inner product with z, this gives us a 1, so here we have a 1, plus, and now we have here phi z y, so that's perpendicular to x by assumption, and phi x and y, x is in C, phi x and y, yeah, that's also perpendicular, so that all vanishes. So what we get is that rho is also constant now in direction of the maximal holomorphic subbundle, and we put these two statements together, so call these 1 and 2, so from 1 and 2 we get that rho is constant. Here I use the assumption that the hypersurface is connected. Okay. So n equal to 3, n greater equal to 3 seems to be somehow crucial. But why? So in the next step, I want to give another characterization of contact hypersurfaces. From which we can probably easily see what happens in the case when n is equal to 2. Well, this is a proposition 2. So suppose m to n minus 1 in m bar n, usual assumption, connected real hypersurface in Kaehler manifold. So we have this situation, then m is contact hypersurface precisely if there exists, again I have to write all this as smooth, and everywhere non-zero function rho on m such that a phi plus phi a is equal to 2 times rho times phi, where a is the shape operator of m. So where a is the shape operator of m. So this somehow relates the contact condition to some condition on the second fundamental form. And that's also quite so how do we see this? So the eta so in an earlier proof I calculated the eta in general. Yeah? So what we get here is the eta of xy is g of y napper x psi minus g of x napla y psi. It's just using the definition of the eta, writing this out, and one comes up with this expression. But then you see psi is j of the normal vector up to a sign, j of normal vector. This is tangential. We can replace this by the covariant derivative of the Kaehler manifold. J is parallel with respect to that. We can pull out j, yeah, and then put it on the other side, and then take tangential component of this. So what we get is that this here is just phi times a times x. Yeah, we pull out the j here, then we have the covariant derivative of the normal vector with respect to x, and this gives us the shape operator. Yeah, so you put this together. So this is g of a phi plus phi a x y. Yeah, and then you see straight away the relation. Yeah, but I mean that this is true. Contact means there exists such a function, and then we get precisely this condition. And conversely, if this holds, because this expression relates to the eta, we just get the contact condition. Yeah? So one can express the contact condition in terms of a condition of the second fundamental form or shape operator in phi in a nice way. This is very helpful. And this, see, first I was thinking, why can't one say much about the case when n is equal to 2? But this actually tells us what happens when in the case n equal to 2. See, n equal to 2. Right. Maybe yeah, what does this, yeah, m equal to 2. So when we apply this equation to xi, so what we get here, phi xi is 0, phi xi is 0, so we get phi times a times xi is 0. So this means that a xi must be in the kernel of phi, but the kernel of phi is just the span of xi. So this means that xi is a principal curvature vector. Yeah? So xi is a principal curvature vector. So this means that the orthogonal complement is also invariant under the shape operator. So the maximal holomorphic subbundle is invariant under the shape operator. Now when we are in dimension 2, this maximal holomorphic subbundle has just complex dimension 1 or real dimension 2. Yeah? So if you take a principal curvature vector there, x, then of course jx or phi x must also be a principal curvature vector. Yeah? So this equation must be satisfied always. Not always, but if this is satisfied, then you get, so what am I going to say? Maybe I should write this down. So a phi plus phi a is equal to 2 rho of phi. So this tells us that phi a xi is equal to 0, because this and this vanishes. So what we get is that a xi is equal to alpha of xi, yeah, for some function alpha. So where alpha is just g of a xi xi. So this is, we've seen this earlier, this is a definition of Hopf hypersurface. So M is a Hopf hypersurface. Okay. So when we now take x in C and assume that ax is equal to lambda x, and we apply this equation, what does this tell us? A phi, so we get here a times phi x is equal to plus phi times, I put this on the other side, so I get 2 rho, and then I get here a minus lambda times phi x. Yeah, so if x is a principal curvature with principal curvature vector with principal curvature lambda, phi x or jx is 1 as well. And this is the corresponding principal curvature. This actually tells us also something about the mean curvature. So what is then the mean curvature? So the mean curvature will be, we have to just to add up the principal curvatures. Here we get an alpha plus, and then all the other principal curvatures, lambda plus 2 rho minus lambda. Lambda cancels, so we have 2 times 2 rho, and so on, and so on. Yeah, so what we get is 2 times n minus 1 times rho. Yeah, so that's an expression for the mean curvature. Yeah? Yes. So now what can we say about the case when n is equal to 2? N is equal to 2, so we know it's a Hopf hypersurface. So for example, look at the case, shall we take the case m is equal to CP2. Yeah? So there is a nice result which says that the Hopf hypersurfaces are precisely, that's equivalent to tubes around a complex submanifold, but in CP2 this would be just a complex curve. So in this case what we do is here we take a complex, say S or a S complex curve in CP2, and then look at the tube around this. I mean, for small radii and locally, that's all well defined. Yeah. So we take the normal vector, apply J to this, we get this Hopf vector field, or this psi, and that's always a principal curvature vector when one starts with a complex curve with this construction. Yeah. So then, what happens then? So this condition is satisfied, and then we have 2 more principal curvatures and 2 more principal curvature vectors, x and phi x. But so this condition must be satisfied well, it's always satisfied, because if x is a principal curvature vector, phi x is a principal curvature vector, just because A is self-adjoint, yeah? So the principal curvature vectors are orthogonal, so it's always satisfied, this equation. So A phi plus phi A must always be a multiple of phi. Yeah? So assume, in this case, we have AX is equal to lambda x. So then we know A phi x must be equal to mu times phi x. So we add up phi ax plus A phi x is equal to lambda plus mu times phi x. And that's the equation we have here. Yeah? So 2 times rho is just the sum of the 2 principal curvatures. So in the case of Kaehler surfaces, when n is equal to 2, there is really a big variety of contact hypersurfaces. So it's only restrictive, really, when n is greater or equal than 3. So if we take all this here, so this is m bar, and then this is m is the tube. So m generically is a contact hypersurface. So m is a contact hypersurface. Yeah? Generically, whenever it's defined. That's right. So what we actually need is lambda plus mu is, so we should not start with a, probably is it the minimal, so no, I don't know. Well, there is a condition. It's a technical condition. But generically, this is non-zero. Yeah. Okay. Huh?
Generically no constant?
Yes, also generically it's non-constant. It varies from, yeah. This is because you can calculate the principal curvatures of the tube from the principal curvatures of S, and says somehow lambda minus lambda, and so they vary from point to point. It depends really on how you choose S, because the principal curvatures there vary. Yeah. Right. So there is a good explanation why this is a good assumption. Okay? N greater equal to 3 from now on. So the next where am I now? Proposition. Well, let me call this proposition 3, because that's a general statement, proposition 3. That holds for any contact hypersurface here, and that's proposition 4. So assume this is contact hypersurface. So then one can prove a nice quadratic equation for the shape operator, which involves the curvature of the ambient manifold. 2a squared x minus 4 times rho times ax plus 2 alpha rho is equal to, take the curvature tensor of the Kaehler manifold, insert j of the normal vector, j of x, and take the orthogonal projection onto the maximal holomorphic subbundle. So proof, I don't want to write this down, it somehow uses Kodazzi equation and curvature identities on Kaehler manifolds. So it looks a bit abstract when you see this for the first time, but it is very useful. So for example, is choose a principal curvature vector. So choose x in the maximal holomorphic subbundle or in the contact distribution with ax equal to lambda x, so a principal curvature vector. So this then tells us, yeah, actually I need an x. This tells us that 2 lambda squared minus 4 rho lambda plus 2 alpha rho times x is equal to this expression, this curvature expression. So it gives a quadratic equation for all the principal curvatures, and you can calculate this explicitly when you know the curvature tensor of the Kaehler manifold. Yeah? When you have a good expression for the curvature tensor, you can do explicit calculations. Yeah? So this then gives restrictions on the principal curvatures. That's why this is a really useful equation. So the proof is technical. It's 2 pages. I think it's not so nice. Right. So another nice result, just somehow find. You see the trace or the mean curvature is determined by alpha and rho, right, on any contact hypersurface. So mean curvature is determined by alpha and rho. And when n is greater or equal to 3, now rho is constant, so this is a constant term. Yeah? So the mean curvature of a contact hypersurface is constant precisely if this principal curvature alpha is constant. So you see, this tells us the trace mean curvature is constant precisely if alpha is constant. So how can one see when is alpha constant? So we have the usual assumption. Contact. So then alpha is constant precisely if Jn is an eigenvector of the normal Jacobi operator at every point. See this, so if we keep this variable here, so this gives us this is a self-adjoint tensor field, a Jacobi operator. So this has eigenvalues. Yeah? And of course n is an eigenvector with eigenvalue 0. Jn in general is not an eigenvector of it. Yeah? But one can work out that Jn is an eigenvector of this Jacobi operator precisely if alpha is constant. So this gives a curvature condition which sometimes is easy to check, sometimes is not easy to check, but some condition which tells you when alpha is constant, just by a curvature condition. Can I do this proof? No, I don't want to do this proof. It uses some calculations, but let me see. No, I think you should believe me that this is true. And then the main proposition to assume that we have a contact hypersurface. So then for all x in the contact distribution, the derivative of the mean curvature in direction of x is given by the inner product of the normal Jacobi operator with respect to n applied to Jn, and then inner product with Jx. So one can calculate, that's quite surprising, one can calculate the derivative of the mean curvature in the contact direction by simple expression using the curvature tensor. Now the proof of this is, that took me very long, and uses quite some elaborate curvature identities on Kaehler manifolds, but the basic idea is proof, so just the idea is you differentiate the identity phi a plus a phi is equal to 2 rho and phi. So when you do this, you get expressions, covariant derivative of phi, we know this, yeah, we can calculate this, covariant derivative of a, so it's the covariant derivative of a, and that's all we get here. Rho is constant, and then what one does is differentiate and then contract resulting equation. There one uses somehow equations I established before, which relates to the curvature tensor. So when you contract curvature, you get the Ricci tensor. So this then gets the Ricci tensor of the Kaehler manifold involved, yeah, and then there's loads of calculations, and in the end, this comes out. But the final upshot of this is, and that's what I want to finish with, is proposition, where are we now, 7? Oh, it's actually 2 propositions. So we have a contact hypersurface. So then the mean curvature is constant precisely if Jn is an eigenvector of the normal Jacobi operator everywhere. So this is what one can conclude from this equation. Is this right? The bus is leaving at 5:05. So I think I should better stop here then, that we all get the bus, and I have a second lecture, so I can actually start from there again. So thank you for your attention.